Here are solutions to homework set number 4 for ECE 376 Embedded Systems. This homework looks at C programming and the LCD display. Now the first problem is trying to find out how long it takes for C code to execute. One way to do that is pick a pin you're not using on your pickboard and toggle it. In this case, I'm going to count on port C, which is the same thing as toggling port C pin 0. So what I'm going to get out is every time I loop, I toggle 0, 1, 2, 3, 4. If I measure this time, that's twice the period. If I measure the frequency, whenever the frequency is the period, so the number of clocks, this guy right here, is 10 million, because the PIC does 10 million instructions per second, divided by 2, I've got 2 toggles per cycle, times hertz. So if I go over to MPLAB, take this code, compile it, download it, and then run it, here's what I see. I've got this going to a speaker. There's my frequency. It's kind of high. If I go over one pin, each pin is divided by 2. Come on, guy. Here's another divide by 2. Anyway, I can measure the frequency that way. Here, mousey. There's my mouse. So doing that, I measured the frequency as 1149 hertz. To get the number of clocks per cycle, I take 10 million divided by 2 times hertz. That's 4348 clocks. That's to go through the whole loop. The way the code works is every 128th loop, I toggle port C. So the time for one loop is this number divided by 128, 33.97. So basically it takes you 34 clocks to go through this loop, or counting mod 128 takes about 34 clocks. Now if instead I count mod 127, same procedure, I get 240 hertz. In terms of clocks, 20,000 clocks for the whole loop, divided by 127, 127 loops per toggle, 163.97. Takes about 164 clocks to count mod 127. So basically powers of 2 are really easy to count. Something that's not a power of 2 is really hard. So that's oftentimes in programming, you try to keep everything as the power of 2. Makes the programming a little bit easier. It's easier on the compiler. Part C. How long does it take to do a floating point multiply? So let's try it. If I make a the square root of 3, b the square root of 2, c is a times b, keep looping it. Now I'm dividing by 16 just because it takes a lot of time. I want to speed it up some. I'm getting 252 hertz. Throw it in, 19,000 clocks for the whole thing, divided by 16, 1,236 clocks to do a floating point multiply. So basically we try to avoid floating point operations if you can, because they're really, really slow. Just for fun, let's do a floating point square root. Same procedure. Here there is no counter, so it's just divided by 1. 22,000 clocks to do a floating point square root. That's kind of impressive. With the PIC, all you can do is add, subtract, times 2, divide by 2. Given that, find the square root. You can do it, but it's 22,000 lines of code. So basically we don't do square roots in assembly. But anyway, that's problem number 1. Problem number 2 looks at a stoplight. So back in assembler, we did a stoplight. I'm going to convert that code to C. I'm going to count mod 14, which is kind of inefficient from the last problem, but good enough. As we go through the count, on the first count, I'll turn on the green light. Then it goes yellow, then red, and the other direction goes red, red, green, yellow. If I compile that code, project build, download it, Try that again. Hit reset, program. I get my stoplight code. So currently this is going green, yellow, red. Other direction is now green, yellow, red. And here's my counter. 4, 5, 6, 7. So I can do the same thing I did in assembly. In C, it was much, much easier to program. That's kind of like I just have count mod 14. If the time's 0, here's what I do. There's other ways to program it as well. The net result. Okay, where's my code? Here we are. Net result is when I compiled it, it was 530 bytes divided by 2, 265 lines of assembly. In assembler, we did that in 72 lines of code. So the C compiler, they claim it's 80% efficient, meaning the C code is only 20% larger than assembly. Like most manufacturers, they lie. Here the C code is 268 times larger, or 268% larger. But the code is much easier to write. That's the trade-off between C and assembler. In C, it's much easier writing the code, but it is going to be a lot larger, a lot slower. Next, problem 4. In problem 4, we're going to try to turn our pick into a roulette wheel. So here's what I wanted to do. When I press RB0, that spins the wheel, that generates a random number. The ball then spins, showing up on port C, as well as the LCD display. So here we're going to be using the LCD. There's the current position of the ball. Every time I play, I bet $1. If I lose, my bank goes down by 1. If I win, which in this case the winning number is always lucky 7, I gain $8. So how do you write that program? Now, a big part of this problem of this homework set is you don't write the program all at once. If you're a little Mozart, you can do that, but typically what happens is the program just crashes and you get really, really frustrated. So let's go step by step. The very first thing I want to do is get the display routine to work. I need to get something that I can see, so get this part to work. I want to display here's where the ball is, here's what my bank balance is. So to start out, I'm going to come up with a subroutine called display. I'm going to pass to it my bank balance and where the ball is, display that on the LCD and on port C. To display it on the LCD, I'm going to use the LCD move to row 0, column 8. That's right here. There's row 0, column 8. That's where the ball is. Display that as 1 digit, no decimal points. Go to the next row, row 1, column 8. Display the bank balance as 3 digits, no decimal points. So there's the 3 digits by bank balance. Get that to work. Now to get that to work, I'll write a little short test routine. I'm going to say my bank balance is initially 10, the ball's at position 3, display it. And let's see if that works. So again, here's my display routine right here. Does it work? So what I'm going to do is come on, puppy dog. I'm going to have the ball move every 500 milliseconds and display it. Check my display routine. So if I compile it, project build, project build, download the code, hit reset, download, so the code's still downloading, There it is. I can see that the display routine is working. The ball position is showing up here on the LCD, and it's showing up down here on port C. Okay, so far so good. I've got a working display routine. Now let's do a random number generator. I'm going to call a subroutine called spin wheel. When I call it, it returns a number between 0 and 8. Now there's a couple of ways of doing that. One way is to use the person as the random number generator. I'm going to wait for it to hit the button. When I press it, I then count really, really fast mod 8. When I release it, whatever the number is, that's my count. That's my random number. So if I try that, I'm going to go over here. Okay. I'm going to check my random number generator. Let's see. So I'm going to call it, return a ball, display the ball. That's my random number. And I don't really need this. Compile. Download. Code is still downloading. Notice what I'm doing is I'm going step by step. I have the display routine working. Now I'm going to get a random number. Press, release. I got the number 2. Press, release, 0, 6, 4. Okay, so it looks like a random number between 0 and 7. Looks like that routine is working. Okay, next. Next. Can I get the ball to move around the wheel? So what I'm going to do is now set up a for loop. I'm going to generate a random number by pressing the button. That's number 0 through 7. I'm then going to count from 0 to 32 plus n. So 32 is the ball goes around the wheel 4 times and stops at a random spot. Each time I count, the ball moves by 1 space, mod 8. I'll then display here's the ball, wait 200 milliseconds. See if that works. Okay, the code has now been compiled and downloaded. Here it is. I press release and see the ball moving. It goes around 4 times. Also displayed up here. It winds up on number 1. Try it again. Spin, it goes around 4 times. Then stops at a random number. Stops again at 1. I get a little bit nervous. Is 1 always going to win? Okay, this time it was 3. Okay, so that seems to work. Next, can I get it to win on number 7? I'll modify the code and say if it winds up on number 7, I win. I gain 8, otherwise I lose 1. Let's see if that works. So downloaded the code now. When it stops, if it hits number 7, my bank will go up by 8, otherwise it goes down by 1. So there I lost, came up as number 4. Try it again. And lost again, 3. Could go a while. Eventually I'll get a 7 and I win. Okay, so that part of the code seems to work. Now, let's get it to beep. Every time I go by, it'll go beep, 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 beep. Come on with the subroutine. I'm going to toggle 20 times, that's 50 milliseconds, and adjust this number until I get 200 Hertz. In the main routine, I just sit there, throw in a beep subroutine now, every time I go by. Compile, download the code. There's my 200 Hertz. You check with the Piano Tuner app. about 200 Hertz. Okay, so I got that working. It now beeps. Next, I guess at that point you're done. You have a roulette wheel. So I can sit there and try to get winning numbers. Lost 3 times in a row. Yep, still losing. When all's said and done, I have 3,088 lines of assembly. So that is 1,544 lines. Try that again. 3,088 bytes divided by 2, 1,544 lines of assembly. I really don't want to write this in assembly. C really wasn't too bad. That's part of the reason for using C. C really frees up what you can do. You can do a whole lot more in C than you can in assembly. It's at least a whole lot easier. But the cost is the code is like 3 to 10 times larger. The other thing to note about this homework is if you want to do something like a roulette wheel, you don't go out and program it right away. This is an example of top-down programming. You want to get it to work step by step. Start with the display routine. Can I get something to display so I can tell what's going on? Then start adding features one at a time. When you're done, we got this working in 16 minutes, 33 seconds, according to the YouTube video. Again, a whole lot faster than trying to write everything all at once. If you're really good, you can sit there and write the code in your mind, write it all at once. Typically what happens is the code crashes. If you go step by step, it's not too bad. But anyway, that's homework set number 4 for 376. Let's do one more time. Lost again.